Okay, welcome to the NUPOC video study guide number 11. We're going to go over the last part of question 8 here, which is just asking for a brief discussion of the Laplace transform. And I've written out most of the discussion points that we're going to go over just to help this go a little bit faster. But like the last two videos, the Laplace transform is another mathematical tool that we can use to analyze functions by transforming it. So in this case, what we want to do is we want to take a function in the time domain. So let's say our f of t here. And when we take the Laplace transform of it, we're going to, this is what this little bracket is with the capital script L is. That's saying we're taking the Laplace transform of f of t, right? We're just going to take the integral from 0 to infinity of that time domain function times e to the minus st, and we'll take that integral with respect to t, and we'll get this function capital F of s. So if you do this with some common functions, these are essentially some of the more common Laplace transforms. And this is sort of, right here, this is sort of what's included in the solution manual. This is essentially all they do is they list the definition and then some of these transforms. But what's really great about the Laplace transform is these two properties over here. That if you take the Laplace transform of some, the derivative of some function f of t, what you'll get is just s times the Laplace transform of that function minus some initial condition. And if you take the Laplace transform of the integral of some function, you'll just get 1 over s times the Laplace transform of that function. So this is really great because for me as an electrical engineer, when we want to look at complex electrical systems, say with a lot of inductors and capacitors, what you end up getting when you write your node equations or your mesh equations is a set of many simultaneous differential equations, which can be very time-consuming and frustrating to solve. But what we can do is we can take the Laplace transform of those equations term by term and replace all these differential operators or integral operators with just s or 1 over s. So now what we've done is we've gone from a differential equation in the time domain to an algebraic equation in the frequency domain. And since we're usually interested in the frequency response of a system from the input to the output, we're not really losing much by going to the frequency domain. If we were looking in the time domain, one disadvantage there is we can really only look at one frequency at a time, and we have to solve all these simultaneous differential equations, and what we get is a time domain signal that is growing and then decaying or oscillating or what have you, which is great because we get to look at the actual waveforms. But oftentimes what we're interested in is the response of the system over a range of frequencies. And so being in the frequency domain allows us to do that. So oftentimes what we'll do is we'll have a circuit and we'll go to the frequency domain and we'll do some algebraic manipulation and we'll solve it for, say, if we're looking at some system and we have an output voltage and an input voltage, maybe we have, let's say, V out of S over VI, it's the V input of S. We'll call that our transfer function T of S, and maybe it looks something like this. And so what we have here are a series of zeros and poles in our transfer function, and we can use these to easily develop a magnitude and phase Bode plot and analyze the frequency response of the system, which is very convenient, and that's often what we want to do. So the Laplace transform is a great tool for going from complicated differential equations in the time domain to much simpler algebraic equations in the frequency domain, and then developing frequency domain transfer functions. Just a quick comment on the inverse Laplace transform. Typically how we do that is we do some sort of partial fraction expansion on our capital F of s, or in this case our capital T of s, and we try to break it down into recognizable capital F of S's. So something, say, over from this column here, or if you had a longer table, there's lots of other common Laplace transforms. And so you would break, in this case, T of S down into a sum of lots of different terms, where each term is something that you can recognize and has the same form as something in a Laplace transform table. And then you just go and you take the inverse Laplace transform via the table. So that's basically a quick summary of the Laplace transform. Again, it's a tool that we can use to go from the time domain. Let's take a time domain function, translate it into the frequency domain, which is very convenient in certainly a lot of electrical engineering applications, but also the same is true for any system with frequency dependent components. So you see this in control feedback, where often an integrator is just indicated as 1 over S, differentiator is just S. And of course in mechanical systems, where you have perhaps beams and trusses that can be represented with masses and springs and damping and that sort of thing. So it's a very convenient tool, finds a lot of applications in engineering problems, really thanks to these properties here, which really allow the simplification of differential equations.